All right. We'll go through types of ligands, and we'll talk about ambident ligands, bident ligand, keratin ligand, neutral ligand, weak field ligand, strong field ligand, polydentite ligand, and tridentite ligand. So we'll go through all these type of ligands with example. All right. Okay, so that is it. So suppose we are given, so we need to understand what a ligand is. What is a ligand? Okay, what is a ligand, by the way? So a ligand is just a molecule or an ion, all right, which bound to a central metal atom or just metal ion. Okay, so suppose this is the cobalt, all right. So a ligand will come and bind to the what? To the central metal. So let's say this is a ligand. Okay. So that is what we call a ligand. Okay. So a ligand is just an ion, all right? Ion or a molecule, all right, that bind uh that bind uh or which bind to a central um metal ion or atom. Right. So this metal can be an ion or just a normal atom. All right. So that's about um, 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 a ligand. So it's the one which will just is an ion or a molecule that will bind to a central metal ion or just an atom. So what will happen? We have demonstrated how it will be happening. And this is the type we have talked about: ambidentate ligand, bidentate ligand, keratin ligand, neutral ligand, weak field ligand, strong field ligand, polydentate ligand, and tridentate ligand. All right, so those are the types of ligand that we'll be talking about. So let's start them one by one. We'll be even giving example. So a question, I say a question to say define each of the following and give an example. So we'll be there now to answer such questions. I'll show you at the end if at all be available to show the answer. All right. So what we'll do is, so we said a ligand will now what bind to a central. Let's say for a tetrahedral, I will write like this. All right. Let's say a ligand will bind here. Let's say fluorine. All right, fluorine, 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 like that. So this is the type of what complex that we have. All right. So it's what it is. It is octahedral compound or just the complex. So these guys are what we call now ligands. So are the one which binds to the central metal ion. So they had a negative of, so that negative is the one which has binded to that, and you're able to see this bond forming. So that's about to a ligand in coordination compounds. All right. So what will happen is that we have a lot of them and different types. So let me start with one. So there's what we call a all right, monodentate ligand. Okay. So what will happen? What is this monodentate ligand? We'll give an example. So 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 a monodentate, dentate simply means donating, all right, or just binding. So this is the type of ligand which bound to the central metal atom or ion through a single donor atom. So it will be just using one donor atom. So we'll say a monodentate ligand is a ligand that bind to the central atom, to the central metal ion or atom through a single donor atom. Suppose I have, so if I were to write, I'll be very late. So let me just explain. So a monodentate ligand, we said, suppose I have, So it just uses one ligand to bind to the central atom. Be a molecule, all right? So if I light NH3, this guy can't donate this hydrogen. Only this guy would donate through those pair of electrons. So what will happen is that these ones are the one now which will be used in the bond, all right? So these ones will be used in the bond. So what will happen is that these guys are the one which what will bind. So it can't use hydrogen to bind to a central metal ion, only nitrogen. So it uses one guy to bind to a what? A central metal ion. So we'll have such a case like that. All right, let's say for tetrahedral. So for tetrahedral, it will be just like that. Okay, so I'm even making a mistake. Nitrogen is the one which is supposed to be binded to the central atom. So it only uses one guy to actually make a bond with the central metal ion or just an atom, just like that. So by this is a tetrahedral shape, and this is what we mean when you say um, a monodentate ligand. So it uses only one type of ligand to donate to the central atom as the bond is being formed. So I can give some examples such as H2O. All right. So H2O uses oxygen. What else? Um, we can also give the same ammonia, all right? It uses only hydrogen, I mean nitrogen, no, instead of hydrogen doesn't take part. Even hydrogen doesn't take part in these cases. So we can also give such as fluorine, all right? This group 7 element or just halogen. So fluorine, it use itself fluorine. Then we can have also iodine. It uses itself just like that. We can also have amine. All right, so amine with two there, it also uses this guy there. So that is about to monodentate ligand. So if you are asked and given an example, this is what you should do. Okay, hope that is clear. We said the monodentate ligand is a type of ligand which bound to the central metal atom or ion through a single donor atom. All right, so that's about a monodentate ligand. So let's go and talk about a bi now. So a bidentate ligand. So what is this? A bidentate ligand. So this is just the other example of a mono. It's just the opposite of mono. So in this one, what will happen is that the ligand will bound to the central metal atom or ion through two donor atom. All right. Suppose this is a metal that we have. All right. So a certain ligand. Let me get one of the ligand. So let me light C again. See there. All right. Then I light double O there. Acetate, oxalate. So I'll write oxalate there. So what happens? This is it will use these two guys to bond. You see. So oxalate is like this. So it will use these two guys to bond to what? The central metal ion. So dentate simply means those things that goes to the what? To the metal. All right. The we can say the lines that goes to the metal. So in this case is dented ligand. So so meaning there are two which are binding to the what? To the central metal ion, and that's what we call um a dentate ligand. So for this case, this guy is called just this guy, all right? Not excluding metal, it will be oxatate. Okay, oxatate, oxatate. So this is the oxatate that we have here. All right. So when you see this, something like this, all right. So like this is what we call oxatate. Okay. So oxatate is one of the bidentate ligand whereby it uses two donors to actually bind to the central metal ion or a molecule or just atom. All right. So that is about um, That is about to bidentate ligand. So we'll now go to what we call polydentate ligand. All right. So when you say poly, again, this is now advancing a bit. All right. Okay, so we are talking about polydentate ligand. Okay, what is this? All right. So a polydentate ligand is actually a type of ligand, all right, in which a type of ligand which bound to the central metal atom, all right, or ion through several donor atoms. So it will have a lot of donor atoms. Okay, this is just the case. For mono, it uses one, di two, poly meaning it uses several donor atoms. So a type of um, a type of donor atom which uses, or just is just a type of a ligand which bound to the central metal ion or atom through several donor atoms. So that's about polydentate ligand. So it uses a lot of ligand. Suppose the example that I can give is, or let me just light that. So the example that I can give is um best. So we said a polydentate ligand is a ligand which bound to the central metal atom or ion through several donor atom, all right, through several donor atom or ion, e.g., E, G, T, A, okay, ethyl ditetraamine or acetate, all right. So when you see EDTA, we call it ethyl, all right, diamine. So ethyl diamine tetra, all right, tetra acetate, all right. So that is EDT. So we can give the structure of this guy. So it has it's just composed of its mirror image at the same point. So um uh this is amine, all right. That's the reason why you call it tetradiamine. So this is ethyl, all right, ethyl diamine. So amine, when it is inside alone, it is called amine like that. So diamine, so amine two there, all right. Ethyl diamine tetra, tetra acetate, all right. So what will happen is that we have ethyl there, all right. So I'll put ethyl meaning there are two methanes, all right, all right. So di meaning sometimes you can call it 1,2 diamine, ethyl 1,2 diamine, because we have one there and also two at that point. So you can also call it ethyl diamine when it is just like this, all right. When it is just like this, we can call it ethyl amine. Okay. So now that I have tetraacetate, so I'll put two acetate there, all right. Okay. So I'm putting two acetate there. So I'll put carbon there, carbon there. I mean carbon there, and also carbon there, all right. So it's just a mirror image of each other. So what I'll do is here I'll put oxygen, oxygen. Then, by the way, before I even do that, I'm just trying to show you the picture of EDTA, ethyl diamine tetraacetate. So what I'll do is I'll write here, since this is just an ethyl, all right, which makes up what? Acetate. So acetate will have a negative charge there. So I'll also put the same acetate there. All right. But before that, I need to put some hydrogen there, isn't it? So we put hydrogens there, then oxygen, oxygen, negative like that. So the other thing that we can also do is just a mirror image of each other, all right, of the other side. So this is the other, but don't show this mirror image. I'm just showing you how you can master this. So 0, 0, all right. But let me put some hydrogen there, all right. So some hydrogens there will be there, all right. So and also here some hydrogens. So what will happen is that I'll bring these oxygens which are there. Then I'm done. This is what we call a polydentate ligand, a ligand that bound the central atom through several donors. Okay, hope that is clear. Through several donors. Okay, so that's about a polydentate ligand, and also this is the best example. You can give the example EDTA. So that is it. So if we were to talk about optical, and also this can undergo optical isomerism, I guess. But we'll talk about those things later. Geometrical isomerism, we'll talk about those later. Okay. So now the other thing that we can talk about is what we call a kerat. All right. So a keratin ligand, what is a keratin ligand or keratin ligand? It's just the same case. So a something which is keratin is something which is trying to make a circle. A keratin thing will try to make a circle in the process. So that thing which will try to make a circle, we call it a keratin. All right. So it may be this keratin. It may be poly dented ligand or bidented ligand. So bi it uses two, right? We saw for bi that we had something, all right, which actually use the two things to bind the central metal, all right. Let's say these are something for bidentate. Again, for polydentate, by the way, let me just take you back for on the polydentate ligand. So here what will happen is that these are what these are the donor atoms. So there are several of them, all right? So what will happen, they all want to bind to the central metal atom. So what will happen is that we'll have 1, 2, 3, 4, all right? By the way, there are also other electrons there and also other electrons there. So we call them, because nitrogen needs supposed to be bounded to four things, and we have 1, 2, 3 so far. So what we are going to do is, in short, we have 1, 2, 3, 4, 5, 6. So this is hexa in terms of ligands, just or donor atom. Hexa what? Dented ligand. So this is the hexa dented ligand. So meaning that there are 6 ligand that should what bind to the central metal atom. In short, there are several. All right. So that's about um, so once these guys they bind to the central metal atom, if they were to make a keratin like that, a keratin now they will make a circle. And one thing we need to know about keratin things, they are more stable because they are making a circle, and it's not easy for you to what to break the bond that is in the form of a circle. So there we go. A keratin ligand or keratin ligand is the ligand that actually it may be polydentate ligand, all right, polydentate ligand or didentate ligand, all right. So it can be like that. So this thing here, which will actually be like this, but in this case, it will form now a circle, all right. It will now form a circle or just a loop. It will form a loop now. Since it's a bidendant, it can be bi or keratin or just poly. But in this case, the goal is to make a what? A circle. All right, let's say this is a metal, it will bind like that. So it may be poly or di-dentate ligand, but it will form a cross loop, like they'll come close to the central atom like that, all right, and make a what? A loop connecting with a metal. I'll give an example for that. So it can have at least like it can contain a pod one or a di, but not mono, because in a mono you won't see two things binding to the central atom. But in a poly and also di, there are two guys or more that will bind the central atom, like we saw for EDTA. All right, ethyl diamine tetraacetate. We saw that. Okay, so a keratin ligand will look like this. Suppose I have M there as a ligand, all right? So then it will bind like that. So I need at least to make a didentate ligand or a what? A pod. So this what I'm making is now a di, all right? Okay, something like that. So um so it will form one. The best example we can give, we can see there are two. Can we name this compound? All right, like we have amine there. All right, then we have an methane there, which is just methane, right? Again, we have methane there. All right, then we have again amine there. So meaning that we can start numbering one, two, right? So we can start numbering either or the even whatever side you can choose this side or this side. All right, numbering is still the same because they are just two. So I'll start numbering from here. So I'll say now this is making me what? This is giving me what? Ethyl. All right, because there are two methanes that will be abbreviated as ethyl. So I'll say ethyl. All right. At carbon number one, I have amine there. So I'll say 1, comma. Again, at carbon number 2, I have amine there. All right. So this will be diamine. So that's how you can name that example of um, a keratin. All right. So even the same EDTA, which is ethyl diamine tetraacetate, can also be a keratin ligand because it can make a circle. That one we saw that. So this is one of the example for keratin ligand. So they are making um a circle like that. Okay. So the process of making a circle is what we call now a keratin. All right. So the other thing that we'll talk about is now what we call um let's talk about something else now. Let's go. We talk about ambidentate ligand. All right, ambi. So an ambidentate ligand is actually a ligand that can bound the central metal atom. All right. So it can bound the central metal atom. It can bound the central metal atom. All right. Having so it will have more than one donor. All right. So it doesn't depend on one donor like we saw for monodentate ligand, such that it only uses, like for water, it only uses oxygen. But for this one, for this type ambidentate ligand, they'll be using both. Like it doesn't depend on the one side of the molecule or one side of the site. All right. So it will have more than one attachment. All right, site. So a ligand with more than So it will have more than one attachment site. So meaning that uh, um, it will bound to the central metal atom through the what? Let's say we have A and B. This A and B, it can use this guy also to bind to what? To the central atom, or it can use this A to bind the central. That's what we call ambi, all right? Like it uses two things. Umbilical cord, it can be this point and also this point. That's the meaning of umbilical. Just get it in that case, umbilical cord. All right, so you master it like that. Umbilical cord uses the exchange of gases between the mother and the what, and it doesn't like you can't know where minerals. Sometimes the some product are going into the mother, and again some nutrients are coming into the what, into the baby. So that's what umbilical cord, and you can master it like that. So one best example I can give is I can give for cyanide or cyano. Let me just give um for cyanide or cyano. All right. So when it uses we have a special name when it uses, let's say it is bounded to a metal. All right. Again, when we just have through S, there's a way we call it again. All right. So these are one of the type of, again, let's say we have nitrito. All right. So let's say it uses this one. It uses nitrogen at this point. Again, it can also perform like this. Like that. Okay, so it doesn't depend on one guy. It doesn't depend on one guy. It can use on both sides. So these are what? Ambident and ligand. All right. Okay, so that is it about these ones. So if this cyanito or cyanide bounds or make a bond with a centromere through the use of nitrogen, then we'll call this as thios. Okay, thioiso cyanide or cyanito when it is just alone. But when it is just bonded, for this one you call it cyanito, just like that. All right. So we call it isocyanito. So cyanito, you can cyanide, just like that. All right. Okay. So when it is bonded to when it uses S now, you call it cyanito, just like that. Iso cyanide. There's no harm. You write cyanito, just like that. There's no harm so long as it's not the end name. So there's no harm. So that's about ambident and ligand. All right, with more than one attachment site. Okay, so that is it about these ones. So that is about ambident and ligand, and hope that is clear. Okay, so let's go to the other type of ligand as well. Okay, because we're almost there. So we'll go now to what we call okay, so we'll go to what we call now a weak field ligand. So a weak field ligand is actually the type of ligand. Um, this one, they are weak, so they will bound to the central metal atom or ion through the use of I normally make the abbreviation as just to show. All right. So wherever they bound to sulfur, hydrogen, and oxygen, then those ones will be very weak. All right. So in short, they are weak donor atoms. So like sulfur, hydrogen, and oxygen, these are weak donor atoms. So we can have examples. So we are saying that a weak field ligand is a ligand in which donor atoms are very weak. All right. So the donor atom will be sulfur and the hydrogen, sulfur, and oxygen. So a weak field ligand is a type of ligand or is a ligand in which the donor atom is sulfur, hydrogen, or oxygen. So sure, just like that. So in which donor atom are. So we have sulfur, hydrogen, and the oxygen. These are the donor atom that we find in the what? And including group halogens, they are also what? They are also weak ligands. E.g., we have fluorine is a weak ligand. So chlorine is a weak ligand. Bromine is a weak ligand. Iodine is a weak ligand. Hydroxyl is a weak ligand. Cyanide is a weak ligand. So cyanide through the use of what? Not through the use of N, but just through the use of what? We are only interested with these ones, all right? So through the use of through the bond using what? S, because this sulfur we have discussed to show as those abbreviation for weak ligand. Right? So what will happen is that after this, when it is through a nitrogen, which is um, thioisocyanide, then that will be now a strong ligand. We are only interested with the sulfur to have a weak ligand with us. All right. So again, the other one that we can give is um, carbonate, carbanions, something like that. Okay. So this will be now carbonate. Okay, like that. Carbonyl. You can simplify there to get what? Carbon dioxide by carboxyl. Okay, in short, what we are interested is the oxygen. So when it uses oxygen to bind, then we'll have a weak ligand. So say um, these are just examples. These are just examples you can have. So meaning that if it uses oxygen, then we'll have a weak ligand. Okay, that is it. So the other way we can give a weak ligand, even that one we saw for bidentate ligand, all right, the one which uses uh, two donor two donor points, so we call it didentate ligand. So this didentate ligand, we can see that it uses oxygen to bind to the what? To the metal. So meaning that oxygen we have presented is what? Sure. To mean um, it is like that. Okay, so we are no longer, we don't want sulfur, hydrogen, and oxygen. They are taking us to weak ligands. So um, let's go and talk about let's go talk about a strong ligand. A strong ligand. So what is a strong field ligand? But it's supposed to be field ligand. So what is this? Okay, so a strong one. Now these ones will involve. I'll prevent this one as what? PCN. All right, PC. number. All right, let's say you have a PC, then it has also a number somewhere, so we'll call it PC number. So whenever the bond is involved through the use of cyanide or just carbon and the nitrogen, we call it a strong ligand. So a strong ligand is a ligand whose donor atom are P, C, and the N, like that respectively. Okay, so meaning that um so this will be now the donor atom. And I can give an example. Suppose this is now my central metal atom. Then what will bound is all right. So I'll have something like that. Then um I'll put hydrogen there. All right. Okay. Okay. So what will happen is that these are what we call now uh strong field ligand. It uses the what? It uses the nitrogen, not that hydrogen you're able to see. So it uses that to bound to the centromere. So we name this as what? En. So this thing here that we have here, we call it En, or just ethyl diamine. So we call it En sometimes. So when you see ethyl diamine, just know that this is the structure which is being talked about. Or you can call it ethyl, all right? Ethyl 1, 2, diamine. Okay, just like that. So that's it. That's what we mean when you say a strong field ligand and also weak field ligand, polydentate ligand, monodentate ligand, ambidentate ligand, and also let me give you the last one. Okay, so let's talk about a neutral ligand. So what is a neutral ligand? So a neutral ligand is the one which neither have positive or negative charge on it. So we can also talk about, we can give examples such as aqua, which is just H2O, amine, all right. Okay, what else? These ones, they have negative, post as zero charge. So we can also talk about what? Um, Carbonium, this one has this zero charge. So those are what we call a neutral ligand. So they do not have a charge, all right, as their raising power. So they don't have that charge. So their charge is zero. They are neutral. So that's about neutral ligands. All right. So let's talk about also um, something we call okay. We'll talk about tridentate ligand now. All right. Okay, what is this tridentate ligand? So this one, they have three donor atom. Tri is three. Remember we had bi, all right? Two. But for tri, um it will be now they have three donor atom. They have three donor atom. So the best example I can just demonstrate, suppose we have a central metal atom there, all right? And it burns using, let's say, this side, and also this side, and also this side. So this is now that something, let's say this is A at this point, this is B, this is C, all right? Okay. So it make whatever structure it can make, but we just have to know that it uses this point, and also this point to bound to the central metal atom. So that's about to tridentate ligand. They have 3 donor atoms. Okay, so you can give an example, but that's what you need to know about tridentate ligand. So thank you very much for actually attending the meeting. See you in the next topic, where we'll be talking about geometric isomer, optical isomer. All right.